Good evening, statisticians. I decided just to keep on going. So I'm going to do this chapter 9 review right now. I'm going to take off my glasses because my eyes are killing me and I'm going to be staring at the screen for quite some time. So I'm just going to continue. I just did 2 from the chapter 9 review and now I'm going to do the rest of them. So I'll work for about an hour, see how many I can do for you. So here we go. First step is to share the screen. Magic. And I'm just gonna minimize my floating head and get right into it. So here we go. I did numbers in the last video. I definitely need this chart. In the last video, I did numbers 4 and 15 for you. I'm gonna do one as starting from one as many as I can. So here's number 1. So here we go. In the largest clinical trial ever, 401,974 children were randomly assigned to 2 groups. The treatment group consisted of 201,229 children given the Salk polio vaccine, and the other 200,745 children were given a placebo. Among those in the treatment group, 33 developed polio. Among those in the placebo group, 115 developed polio. If we want to use the methods of testing the claim about 2 populations proportions to test the claim that the rate of polio is less for children given the Salk vaccine, are the requirements satisfied? I think it's satisfied because we got 5 and 5. The rates is statistically significant. Requirements are not satisfied. The samples are not simple random samples that are independent. Oh, I like C. And the requirements are satisfied. The samples are simple random samples that are independent. In each group, the sample size is at least 1,000. I'm gonna go with A. See how it goes. Let's see. Nice. So I got it right. That was lucky. So these are the 2 things you need: the sample proportions for 2 random samples that are independent, and for 2 samples, we had at least 5 successes and 5 failures. The first condition is met because they were randomly assigned the 2 groups, and the second condition is met because there's at least 5 in both. All right, let's keep it trucking. Here's number 2. In a large clinical trial, I can make it bigger. That's nice for my eyes. 401,000 were assigned 2 groups. The treatment group consisted of 201,000 vaccine for the disease, and 35 developed the disease. The other were given placebo. 111 those were developed the disease. Consider the vaccine treatment group to be the first sample, A through D. Assume a P01 significant levels, which is better. Hypothesis. I like hypothesis better. I always like it better because we could either say yes or no instead of giving a range. So I'm going to go with the hypothesis test. Let's see if that's correct. Nice. Cool. Just because it's a vaccine, I'd rather not have a range. I'd rather just know if it works or if it doesn't. In general, dealing with inferences for 2 population proportions, which 2 of the following are equivalent? Confidence interval method, p-value method, or critical method? To me, p-value and confidence interval are pretty much equivalent. So I'm going with confidence interval. No, it's p-value and critical value method. Both of these use a standard deviation based on, I'm going the assumption that the proportions are equal or estimated values of the property, whereas the other uses, oh, okay. I don't know. This is a hard question. So I think it's going to be the assumption that they're equal, and this one's going to be the estimated values. Feeling good, getting them all right. I love it. So if a 0.01 significant level is used, okay, so this is the table that I kept forgetting. Good thing I kept it here. We're doing 0.01 and one-tailed. So that means 0.01 and one-tailed, we're talking 98%. Look at me go. Phantasmic. Okay, let's keep going. All right, if the claim in part C, we get a -5 and a negative, what does this mean? Because the interval does not contain 0. All right, because we're doing a confidence interval. There appears to be a significant difference. because only values less than 0, it appears that the first proportion is less than the second proportion. There is sufficient evidence to support the claim. That was a lot. Let's see if that's right. Sweet. So if that was too hard for you, I guess rewind it. Sorry I did it so fast. All right, question 3. A study was conducted to determine the proportion of people who dream in black and white instead of color. People do that? Wild. Among 308 people over the age of 55, 67 dream in black and white. And among the 294 people under the age of 25, 13 dream in black and white. 0.05 significance level to test the claim that people over 55 is greater. Okay. Okay, than those under 25. So here we go. The first one would be that they're equal, and we're talking greater. So equal and greater, I'm going D. Let's see if that's correct. Cool. I need the Z statistic, so I'm just going to run it. So I'm going to go to stat, proportion stat, to sample with summary. My first one was 308, 67. All right, so the first one is 67 over 308. The second one was 13 over 294. All right, and we're saying that this is going to be a greater than, and I want the critical value at the 0.05 level. Compute, magical. So our Z stat is 2 decimals, 6.26. Let's see if that is correct. Cool. Our P value is 0. Cool. And what conclusions? The P value is less than the C, so we reject the null hypothesis. There is sufficient evidence to support the claim. Cool. All right. So, oh, there's more. There's always more. Okay, so now I have to do a 90% confidence interval at what? The 0.05 level. Okay, so, all right. So what do we need? So we're talking 90% confidence interval. So we're doing 0.05 level, but it's a one-tailed test. So we're talking 90%. So 0.05, one-tailed, 90% confidence. So all I have to do is change options, edit, confidence, 90%. Let's see if this is correct. So our lower limit to 3 decimals is 0.130. Notice the rounding. And the other one is 2.217. Let's see if that's correct. Nice. Cool. All right. And there's one more statement I guess I have to do. All right. Because the confidence interval does not include 0, the two proportions are not equal because it's only positive values. And white is greater than. All right. And okay, so C. An explanation for the results is that people over 55 are exposed to medium black and white. Can these results be used to verify the explanation? No, results speak to possible difference in proportions, but they cannot verify the cause. I'm going B. Difference, but the results are not statistically significant enough. No, they are statistically significant enough, but we cannot use it to verify cause. I like B the best. All right, so number 4 I already did. You can watch it in the other video if you like. So I'm going to number 5. All right, here we go. All right, use the, what does it say? Use the expression in the accompanied discussion of sample size and find each sample if you want to estimate the difference between proportions of men and women who own smartphones. Assume that you want a 99% confidence interval, and your error is no more than 0.04. I'm not sure what to do here, so I'm going to look up an example. So we have to do 1 minus alpha. Okay. I got to use this formula. Okay. We have error to find the margin of error. Okay. 95%, alpha is 0.05. So I have to do z squared alpha over 2 times error squared to get the n. All right. That's a lot. Okay, that's a lot. So I'm gonna have to write that down. Thought I could do it all without writing a bunch of stuff down, but that's okay. So I'm just gonna keep it going with the bottom of the chapter 9. No big deal. So here we go. So this is the formula. The formula is n equals zeta squared alpha over 2 divided by 2 error squared. I think that's all I need. I think that's all I need. Alpha over 2. And they're talking 95% to give me 1.96. We want 99%. So 1 minus 0.99 equals 0.01. Okay. 0.01 divided by 2 is going to be 0.005. That's what I need my zeta to be. So I'm going to actually go to StatCrunch. And I'm going to go to stat calculator. I'm going to go to normal. And now I have the 0 and 1. And I want this to be 0.005. Let's see what that is. So this is going to be, I believe it's going to be 2.58. So that's going to be the top. So I need 2.58 squared. All right, now what else do I need? I need an error which is no more than 0.04. So I have to do 2 times 0.04 squared. I'm just going to put this into delta math so my brain doesn't hurt. So I'm going to go, not delta math, I'm going to go to Desmos, my bad, graphing calculator. So I think this is the right answer. So we have 2.58. Don't worry about the negative sign because we're squaring it. All right, and I'm going to put this here. So when I divide it, it'll look fine. So 2 parentheses 0.04. I got to square this thing. All right, cool. So we have now, I think it's 20,081, but they haven't been rounding up for people, which really makes me sad. So this is what I think it's going to be, 2080 men and 2080 women. Let's see if that's correct. 2080 and 2080. I got it. Wild. All right, next question. Let's keep on trucking. So a professor collected data of eye color and gender of statistics students. Among 884 male, 269 had blue eyes. Among the female that had blue eyes, 0.05 significant claim that proportions of blue eyes are the same for males and females. So it doesn't say that it's greater than or equal to. So one's going to be equal, one's going to be not equal. It's a two-tailed test. Now we just have to get the Z statistics. So I'm just going to go to options, edit. We got 269 blue eyes for 884. And we have 438. Well, a lot more girls in school. 438 of 1125. And we want a hypothesis test with equal and not equal at the 0.05 level. So what is our Z statistic? It is negative 3.96, two decimal places, negative 3.96, negative 3.96. All right, let's see if that's correct. Excellent. Our p-value is just 0. All right, so the p-value is less than the alpha, so we reject the null. There is sufficient evidence to warrant the claim. Oh, disappeared. Awesome. Now we're going to do a 95% confidence interval, but it's two-tailed. So 95%, so we're talking two-tailed at the what? Oh, at the 0.05 level. Yeah, so two-tailed at the 0.05 level is 95%. So they did it for us, which is fine. So confidence interval, 95%, compute. It's going to be, our lower limit is 3 decimals. So negative 0.127. And this one's going to be a negative 0.043. Let's see if that's correct. Fantastic. So because the confidence interval does not 0, then the proportions are not equal. There is sufficient evidence to support the claim. Cool. All right, the professors used what type of sampling? Seems like they're using a convenience sample of their students. Cool. All right, is it likely to be biased? No, the sample type, but there's nothing indicating the prevalence. Yeah, I'm going C. C sounds right to me. Cool. All right, we're up to number 7, flying through this thing. So here's 7. All right, independent or dependent? Data set of systolic blood pressure measurements from 170 randomly selected men and randomly selected women. They seem to be independent. I like B the best. Let's see if it's right. Nice. Doing great. Not one mistake yet. So I'm feeling pretty good. So here we go. Experiment was conducted to determine whether giving candy to dining parties resulted in greater tips. The mean tip percentages are on the table in standard deviations. Assume that the two samples are independent. Okay, simple random. So we're saying that the candy's going to give more tips. So that would be mean 1 is less than mean 2. Mean 1 is less than mean 2, and the null is that they're equal. Okay. All right, so they're giving us data. I might as well open it in StatCrunch so I don't have to actually do it by hand. I guess I didn't need to because it's a summary, which is weird. So I'm gonna just get rid of that. So I'm gonna go to me, this is paired. Because I think that it's paired. So I'm gonna go to tstat, a paired data sample. No, but I need it with not the summary. So stat, tstat, paired. Oh, so paired I have to have the actual values. So I'm gonna go to two sample with summary and see what happens. My mean for 1 is 18.4. My standard deviation is 1.49. My sample size is 36. Here, my sample mean is 20.95. My standard deviation is 2.38, and my sample size is 36. And I want this to be less than, and we're going to do this at the 0.05 level. So let's compute that. All right, so my T statistic here is 2 decimal places, negative 5.45. Let's see if that's correct. That is incorrect. All right, let's see if I typed everything in right. 18 point, oh, there it is. 18.24. That was a mistake. 1.49, 20.95, 2.38. So I just typed it in wrong. We are all human. So it's negative 5.79. So I just typed it in wrong. It happens. My p-value is 0. We are going to reject the null hypothesis. Giving candy does result in greater tips. That's so cool. Give your restaurant goers candy. All right, now we have to test the confidence interval. So we're talking one tail test at the 0.05 level, one tail 0.05 level. That means we are 90%. 90%. So options, edits, confidence, 90%, compute. All right, so we're talking 2 decimal places. So we're talking a negative 3.49 and a negative 1.93. Cool. Yes, because the confidence interval has only negative values. All right, so here's number 9 when it loads, if it loads. All right, I'll just reload the page. Cool. I don't know. It's freaking out. I'm just gonna go to 10 because I did 9 already. You all saw it. So let's see if 10 works. All right, so we're going right to 10. You just saw 9. You can rewind it to watch it again. So listed in the accompanying table, okay, we got weights, U.S. male Army personnel, 1988, and different weights, blah, blah, blah. Assume the two samples are independent samples. All right, cool. Use a 0.05 significance level. All right, so here's our data. Open in StatCrunch. What are the null? So the null would be equal, and we want to say that it is less than. So I'm going A. The test statistic is what? They're saying that they're independent random samples. So I'm going to go to data, stat, t-stats, to sample with data. We got the first one is 2012. We said that, oh, sorry. The first one is 1988. The second one is 2012, and we just want to make sure that it's less than. Pretty sure that's what we want. Significance at the 0.05 level. All right, so let's see what we get. Our test statistic is negative 3.22. Let's see if that's right. Cool. Our p-value is 3 decimal places is 0.002. Cool. We are going to reject the null. There's not sufficient, no, reject the null. There is sufficient evidence to support the claim. All right, now we have to do this one. So because we have a one-tail test and we're talking at the 0.05 level, so we're talking one-tailed 0.05 level, so we need a 90% confidence interval. So here we go. Options, edits, confidence interval, 90%. Let's see what we get. So here it is. We're going to 1 decimal place. So that is negative 18.1. And this is going to be a negative 5.5. Next question. All right, so here we go. Number 11. Hopefully it loads. I don't know what's going on with the internet, but it's trying to load. I guess I got to reload it. Oh, here we go. Here's 11. All right, so assume that two samples are independent simple random samples from normally distributed populations for the data set. Okay, so here we go. That's why it's such a big set. All right, so I'm just going to open this in StatCrunch. Big set of data. Cool. We got women, we got men, they're huge. What are the known alternative? Do not assume that the population distribution are equal. The claim that women and men have the same. Okay, so it's just equal and not equal. So this one should be A. We need the test statistic. So I'm going to go to stat T statistic. I'm going to sample with data. And I'm going to do the first one is women. The second one is men. And we're talking 0.01 level for the critical value. All right, so let's find this test statistic. All right, so the test statistic is negative 2 decimals, negative 0.87. Let's see if that's correct. Nice work. And the p-value is 3 decimals, which is 0.383. Nice work. So we failed to reject it, and there is not sufficient evidence. All right, cool. So we're up to number 12, almost at the end. All right. Listed in the accompanying table are numbers of hospital admissions in one region due to traffic accidents on different Fridays, falling on the 6th day of a month and the following 13th day of the month, or whatever, assuming that we want to use a 0.01 to test the claim that the data that fewer admissions on the hospital due to traffic accidents occur on Friday the 6th than Friday the 13th. What a morbid thing. So the null hypothesis would be that this is equal to 0. All right. So the null, if we want to know that it's more than, so this difference would have to be greater than 0 if we're subtracting them. Oh, okay. Less than 0. I guess the subtraction was wrong in my head. Oh, that was it? Cool. All right. Number 13. The temperature at 8 a.m. in the first sample and 12 a.m. for the second sample. Find the values of D. All right, so what is this? Is that mean of difference? I don't know. I got to see an example. I don't know what they're asking for. Continue. So we have to subtract them. Then we have to add those together. We have 5 here. We have to subtract them all and do what with it? Find the average. Then I have to find the standard deviation of it. Okay, that's weird. Of the differences. Okay. That's the mean differences. Oh my God. All right, I guess I can do that. I'm gonna open it in Excel because there's so many steps. Well, my Excel loads. Well, there's only like 3 to go, so I will do this one, and then I will figure out the rest of them. So it's 13, 14, and 16. All these check marks. It's like I've looked at them before, even though I have never seen these problems. Sometimes you just get lucky. All right, so here we go. So the first thing is differences. So I'm going to put a D here for difference. Oh, enable heading. Sorry. So this is my first step. This is how I'm going to do it to like save time. So this is my difference. So I'm going to do equals the first one minus the second one. And then I'm going to drag this to get them all. So these are all the differences. Now I have to find the sum of the differences. So I'm going to do equals. You can just highlight them all if you don't want to do summation. So the sum is negative 0.9. It's right there in the corner. Or you can do equals sum if you want, or hit the sum button, but either one, we're going to get negative 0.9. All right, so that's the sum of the differences. And then I want the average of the differences. That's the first step. I have 1, 2, 3, 4, 5. So I'm going to do equals this value divided by 5. It's negative 0.18. Negative. Do not round. I did not round. Well done. All right. Now I need the standard deviation of this. So view the example. Okay, so we have the average, but now I need the standard deviation of all the differences. I could just type it, but I guess I'll show you the right way to do it. So we have that. We have the average. Perfect. Now I just have to take these values minus the average over 1 and figure them all out. So basically, we have to take each one of these, I'll do this the right way, and subtract it from it. So this is going to be your D minus D average. So all I have to do is do equals this minus the average and drag it down. And notice if we add these all up, we're going to get 0 because the exact distance away. See, I didn't get 0. Oh, I see what my mistake. So I have to just do this because it's messing it up. So I have to subtract a negative 0.18. Cool. And I have to drag this down. Sorry about that. Now, if I add all of these up, I should get 0. Well, it's close enough. It's close enough to 0. Maybe some rounding happening, but I don't know. All right, now I have to square them all. So square. We'll see if it actually works. Equals this times itself. Cool. And then I have to sum these all. Cool. I might as well just see what this is. Why is it off by 1? So I have this is correct. Minus that makes sense. Minus that makes sense. Minus that makes sense. This is plus. Minus that. Oh, I have an extra one. Oh, I see my mistake. Cool. 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 There was my mistake. So let's drag it one more down. That was adding them all. So this is where our sum is. I don't like making mistakes. This should be 0. Yes, that is correct. I have to square all these. Boom, 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 boom. Perfect. Now if we add all of these up, sum of D2 and D6, and this is going to be equal to the sum of this. We should not get 0. Perfect. And all I have to do is divide this by what? N minus 1. And we have 1, 2, 3, 4, 5. So that's divided by 4. And all we have to do now is equal the square root of that value. Perfect. So this is the standard deviation, the right way, the way that they wanted it. So we have rounds to 2 decimal places, 0.33. Let's see if that's correct. Nice work. In general, what is the mean of this? The mean value of the differences of the paired sample data, the mean of the means of each. No, I like this one. The difference of the populations of the two means. I think it's A. Oh, all right. Means of the no. I think so. Yeah, I think it's this one. Because this means like bigger population. That's like the total. I almost got one wrong. That would have been rough. Two to go if it loads. So we just have 14 and 16 left. I hope this video has been very helpful for you. Here we go. So the freshman 15 refers to the belief that college students either gain 15 pounds or I thought it was gain or lose, but I guess they gain it because they're no longer doing stuff and just eating bad food. Okay. During the freshman year, listed are the weights of randomly male freshmen. The weights were measured in September and then in April. So this is a paired sample data. Yeah, it says paired. Cool. So we're testing the claim that the weights are going to be less. So the first one's going to be equal to 0. Let's say they didn't gain any weight. The second one's going to be less than 0 because they did gain weight. Oh, sorry. I keep forgetting about the subtraction being bigger because this is more weight than before. Simple mistake. So here we go. Here's our T statistic open in StatCrunch. All right, so we're going to go to stat. Sorry. T statistic, paired data. We got September, we got April, 0, and we are gaining weight. So it's greater. And we're going to do this at the what level? 0.0 what? 0.05. Compute. All right, so our T statistic to 2 decimal places is negative 1.35. What? Our T statistic is negative 1.35. Unless I put something wrong. We have September. We have April. We're doing a hypothesis test where this first one is 0. Our difference is going to be greater than 0 at the 0.05 level. All right, so let's see what the mistake is. Our T statistic is negative 1.35. Is it the other way? That wouldn't make any sense. Well, we might as well click compute and see what it is. Negative 1.35. I got the same thing. Saying it's paired data. Paired data. Options edit. September, April. 105 level. I didn't touch it. All right. Well, I don't know what's wrong with it. T-stat paired. We got September to April, and we're thinking that they got fatter, and we want this at the 0.05 level. And I got negative 1.35. All right, let's see what it actually is. Yeah, I know. I'm not going to do it by hand. Why does it have to be positive? Doesn't make any sense. I disagree. I disagree. I disagree. All right, whatever. Our p-value should be the same, 0.8 to 3 decimals, 0.893. I think it's just an error because this should be negative. Is it really the other way? 0.107? What? This is wild. Sorry, I messed this last one up, or second to last one up. Well, I'm not going to argue with it. Since the p-value is less than the significant level, do not reject the null. There is not sufficient evidence. Since the p-value is less than significant level, we do not reject the null. There is not significant evidence. our p-value is less than the 0.05 level. Our critical value seems to be, it's at the 0.05 level though, right? 0.05. Oh, it's because it's greater than the significant level. Oh my God, I just spread it wrong. So it's greater than the significant level. Ugh, guess I'm just getting tired. Sorry. All right, so here's the last one. If you want to see 15, just watch the video right before it. Um, oh, there's more. All right, so construct a confidence interval. So we're doing five one-tailed, 0.05 one-tailed is a 90%. Edit, change this to 90%. I just don't like this problem, but here's the right answer for the last part. So we're going to how many pounds we talking about? We're talking from negative 1.1 decimal place, negative 1.3 pounds to a positive 0.2 pounds. One decimal, negative 1.3 to 0.2. Options, edit, 90% confidence interval. Did I have them backwards the whole time? I think I might have just had them backwards the whole time. I think that's what, I think I just had the months in backwards like a fool. And that's why everything was slightly off. Well, we're about to find out. Negative 0.2, negative 0.2 to 1.3. Let's see if that's right. Yeah, I just typed it in backwards. We all make mistakes since it can suit zero. Do not reject the null. That was the main mistake, and that's probably why. Here, watch this. Now, this is probably why it's going to be the way that we want it for this. Yeah, positive. That's why. That is why it's positive. I plugged in the months the wrong direction. I put September for April, but it should be April over September. This does not address, but it does suggest that there is insufficient evidence to conclude that males gain weight during the freshman year. The confidence interval does not contain a weight of 6.8. Yeah, we're good. We are so good. I just typed it in the hypothesis wrong. That's okay. Last one. I'll take the one mistake all day. That was my error. I put the wrong month in the wrong spot. So listed in the accompanying are 127 measured and reported weights of female subjects, sample data, and the differences have a distribution that is approximately normal. All right, here we go. Here's our data. We're going to see this in StatCrunch. I could actually do this one in Excel. You want to see it in Excel? Probably not, since I did all of them in StatCrunch. So if you want to see it in Excel, just let me know. So here we go. Difference in the population pairs defined by this. So what are we doing? What's the claim? The claim is the measured weights are higher. So females are tending to be higher weights. So the first one's going to be equal to 0 pounds, so no change. The difference, if it's higher, it should be greater than 0. Let's see. Cool. What's the T-stat? So we're going to go to, actually, I did so many of them. I'm going to do it in Excel. Why not see it in Excel? There's one last problem to do. Might as well see it in Excel. As long as it opens. Could have just copied and pasted it. Just so we can see it done in Excel for fun. So here's your data. Boom. I'm going to go to Excel. Just a new page since it didn't want to load. Now it wants to load. Here's our friend Excel. All right, we want the t-stat. So this is paired data for sure. So here we go. So for doing one of these in Excel, you got to go to data, data analysis. They want to do it's a teats test, paired sample for two means. That's what we have because these are going to be the same. So these are paired. It's reported and measured. Our girl's lying about their weight. I'm assuming it's happening. So your variable one is reported. There we go. And our variable two is measured. Notice that I have labels. I just wanted to show you in case you ever type labels. Got to get rid of that. Our alpha is going to be 0.10. And let's just click OK. So here we go. We are doing a one-tailed test. What does that mean? So our t-statistics, the first thing that we want. There it is, 2 decimal places. So negative 2.65. Let's see if that's right. And negative 2.65. All right, let's see what the other one has to share with us. Our fancy StatCrunch friend. All right, so edit, stat, t-stat. We're talking paired. Column 1 is reported. Column 2 is measured. All right. Reported versus measured. Do I have it backwards? So let's first see what this is. And we're talking about the 0.10 significant level. And this one's going to be, was it one-tailed? Was it greater? Yeah, it was greater. That could have been my mistake. Let's find out. So it's negative 2.64, negative 2.65, negative 2.65. So I have it typed in correctly. So obviously, I think the mistake is having it paired the wrong way based on it. So I think that's what my mistake is. So it's going to be positive 2.64. So that was my only mistake here. So if you go back to the sheet we were talking about, all you have to do is go to data, just so I can show you this in Excel as well. Data analysis, paired sample. So our variable one should be the measured. Boom. Our variable two should be the reported. So that was my mistake. I put it in backwards again. That's okay. We make mistakes. Click OK. And there it is, positive 2.65. Well, ta-da, check answer. Good job. Our p-value is, we're talking, it's a one-tailed test. So our one-tailed test is 0.0, how many? 3 decimals? 0.005. 0.005. God bless you. Since the p-value is less than, because we just needed 10, we reject the null. There is sufficient evidence. Excellent. All right, so now we have to do a confidence interval. Notice that we're at 0.10 and we're doing one-tailed. 0.10, one-tailed is 80%. So we want an 80% confidence interval. So I might as well just go back to this for the confidence interval. We can do it on that. My head's already hurting. So edit, I'm just going to click this 80%. And hopefully this is enough to make you feel confident about the class. We want to do it as type integers are 2 decimals. So it's going to be 1.38 pounds to 3.98 pounds. That's how much they were lying about their weight. Not much. So because the confident interval includes only positive values, we can reject the null. So girls were lying about their weight, but only about a pound to 4 pounds. Sounds pretty reasonable. All right, for this, for a random sample of n equals 10 from 127 measured, oh, I gotta be able to read this. Okay, for random sample n equals 10 from the 127 reported weights, a p-value was 0.349, confidence interval was 80%. Did the larger data set have much of an effect on results? Yes. The larger data set caused a p-value to decrease, right? Cause the p-value to decrease. And the conclusion to be change from do not reject to reject. See, like this one includes 0, and that's why we could not reject it before. But as soon as we took more girls into account, as soon as we had more of the girls in it, you knew that enough of them lied for us to change from do not reject to reject. Fantastic. All right, what's next? All right, so we're done. All right, I just did the entire thing. I made one mistake by just going the wrong way. So you really have to make sure when you're doing this and you're seeing what is when you're setting your null and alternative hypothesis, wherever it's greater than or less than, you really have to make sure when you're plugging it into StatCrunch, which one is the first value, which one is the second value, because we're talking about differences of means and subtraction. It really makes sense. That was about it. So I just did them all. Feel free to reach out. I will email this to folks and I'll post it on the YouTube thing. So feel free to let me know if you still have questions, but have yourself a fantabulous evening.